This video is going to start and you're going to think I misplaced it because I'm going to start by talking about the SN2 reaction and stereochemistry. Everybody's favorite topic, stereochemistry. So let's look at this halide. And let's treat this with a really good SN2 nucleophile. Azide's my favorite, but I put azide everywhere. So let's treat this with sodium cyanide. Sodium cyanide tells you definitely do it in SN2. We have a secondary halide, not ideal, but just fine if we have one of our great SN2 nucleophiles. And if we were doing this reaction, the cyanide would attack this carbon. We kick out the bromide. The cyanide attacks from the opposite face of this carbon-bromine bond, and we get inversion of stereochemistry. And the hydrogen, which was back, gets pushed up to the front. And that is our product. And this reaction will work. We get clean inversion of stereochemistry. Oh, very interesting. Okay, well, now let's put this in the context of the SN1 reaction, because the SN1 reaction also has stereochemical implications. So, let's take our same halide. It is a secondary halide, which means when if the halide leaves, it will form a secondary carbocation. Now, if we treat this with something, let's mix this up a little bit. Let's instead put this in water. Otherwise, you think every reaction has to happen in methanol. It doesn't. So, we have water. We don't have a strong nucleophile. However, we have a reasonably okay carbocation. It's going to be secondary. And so what's going to happen is our leaving group will leave. And it leaves behind a carbocation. Now, what do we know about this carbon in the carbocation? It's an sp2 hybridized carbon. I'm going to put the hydrogen in there. It is trigonal planar, which is a fancy way of saying that it's flat. So now, when our nucleophile attacks, and what is our nucleophile? Our nucleophile is H2O. I'm going to draw it down in full. It can either attack, and I'm going to try to shade one of these. Not very well shaded. It can either come in from the top face or from the bottom face. And because it's a planar molecule, there's no difference. So half the time, we're going to form billions of carbocations in this solution. And of those billions of carbocations, half of them are going to get attacked from the top face and half are going to get attacked from the bottom face. So we are going to form a mixture of having the OH, or the water, attacking from the top and the bottom face. And it's going to be a 50-50 mixture. So we get a 50-50 mix of these two. Very different story from what we saw up top in the SN2 reaction where we got inversion. And then I'm going to show this for one of these, not for both. But we will need to neutralize our product. We're not going to finish with these charges. And we'll deprotonate with our water. And it's going to form a 50-50 mixture of these two products. Now, these are substitution products. We've replaced the bromide with an OH. And if we went through and did our R and S stereochemical assignments, we would find that one of these is R and one of these is S. So this is, when you get 50-50 mixtures like this, it has a term called racemic. This is a racemic mixture. It's very different from in the SN2 reaction where it's inversion. This still has a fixed stereochemical configuration. So this is a distinctive feature for the SN1. When you run reactions and you lose control of your stereocenters, that's a sign that you've gone through an SN1 reaction because the trigonal planar carbocation is flat and it can get attacked from either face. That's not true in an SN2 reaction. You always get inversion. So you lose control of your stereochemistry, but stereochemistry is still an important feature in SN1 reactions.